Hi, I'm Greg Kasprowicz. Welcome to my home office. Today I'd like to tell you about our experiment we have at the Warsaw University of Technology, which is MCORD. The MCORD stands for Cosmic Ray Detector for NICA. NICA is an accelerator facility in Dubna, in Russia. What we are trying to do is to make a detector which is looking for cosmic rays, and essentially we are using scintillators which are connected to the photomultipliers. We are not using classical PMTs, but the silicon ones, silicon photomultipliers. This is how it looks like. And here we have a prototype. So inside of this aluminium enclosure, we have a large scintillator which is covered with opaque painting, and then covered with some black tape, and then placed inside of this aluminium extrusion. And there are end caps, 3D printed end caps, but they are sealed. Inside we have several boards. This is the analog front-end board, which is also it has a processor, which has high voltage regulators, calibration circuit, and lots of diagnostics. On the other side of the extrusion we have another front-end. They are connected with high-speed 3M cable. It's a nice cables because they are IDC, I mean isolation displacement connector, and they can be simply quickly crimped, and they run up to 10 gigahertz. So how to use it? This is USB-C cable, and this is used just because it's cheap and it has 4 high-speed pairs. Some of them are optimized up to 110 gigabit per second. We are using it to transfer analog signals. We need 4 pairs. So one pair is analog signal from one end, another pair is analog signal from the other end, another pair is used for calibration pulses, and another pair is simply to connect CAN. CAN is used to manage the front-end settings. Another box, we call it hub because it has 8 USB-C connectors. On the other side it has 2 SAS connectors which go to the FMC TDC module. For the moment we are using adapter which connected to the scope. How to make it running? First you need to plug the power on. Well, this is how you plug the power on. You can use power over Ethernet, it works as well, but we use a power supply to see how much current it consumes. It consumes 300 milliwatts. Next thing, nothing happened on the scope, not much. Next thing is it by default it has a Linux MicroPython processor inside. So it starts with default script. How to open? Once you plug the USB cable, there is a flash drive, and on this flash drive you have just Python script. If you double click on the Python script, they open and you can modify it. This is the code for front end. This is initialization code, and this initialization code has several settings. Let's try to make it working first. You can of course modify the settings, but the easiest part is to open the console, to simply connect the PuTTY, in my case it's COM23 settings, speed setting doesn't matter, opens the console, and here we are, the Python, MicroPython starts, and we can issue comments. Let's first try to make the high voltage off state. We simply put one command with 0, so it will disable high voltage. It's enabled by default, and then once the high voltage is disabled, we can connect the trigger. We simply connect, I don't have a better cable here at home, so we simply connect the generator, which has a square wave, just some frequency, 2.5 volt amplitude, and on the scope we have calibration pulses. The difference between them is something like, let's measure the difference. The time difference is something like 20 nanosecond, 19 nanosecond. It's a difference of the cable length. The calibration pulse traverses from this input, then goes to the LV packet driver, which splits the pulses to 8 outputs. The signal goes to analog front end, and there's another LV packet driver. One side drives this front end, and the other side drives that front end. This is 1.5 meters, so we have twice the 1 height. We have 3 meters of cable length distance. 3 meters times something like 7 nanoseconds gives almost something like 20 nanoseconds of difference. And how the calibration works. Calibrator is very simple. We have a circuit which has cal-in input. There is a 10 picofarad capacitor which is makes a differential circuit, and this D22 diode which simply injects the current pulses to the input of a transconductance amplifier. This RC circuit is simply termination of the LG packet pulses. So calibration works. Let's see how it works with real photons then. So let's switch off the calibration. Easiest one is simply disconnect the calibration pulse. It's nothing here. And let's switch on the power supply. So on the terminal we should simply set this. We should simply repeat the last command and use 1 instead. And the high voltage power supply is on. And let's see what comes out of it. So we have here we have. Let's make the trigger into manual mode, normal mode, and here we have the pulses. The scope is 50 ohm terminated, and this is coupled. There is no AC coupling for 50 ohm termination, so we have to live with these biases. But you can clearly see that there is something. The amplitudes of the pulses are not the same, and you can even also notice that their arrival time is not the same, because photons hit into different areas of the scintillator. Inside of the scintillator there are fibers which are coupled to silicon photomultipliers, and depending in which place of the scintillator the photons hit, then we have a different propagation delay to the photons, to the silicon photomultiplier. So that's why they sometimes the upper one is first, sometimes the lower one is first. Of course, the amplitude also varies because we have different energies of this photon showers. So, how to connect it? To make it running, you need to connect a USB-C cable to the hub. You can, if you put it upside down, nothing will change, will break. The only difference is that the detector outputs will be swapped, and the calibration pulses will be swapped with USB with CAN, so the analog front end won't work. If you simply disconnect, you will get a timeout. Then we have a calibration input. Then you have a SAS cable, which normally goes to FMCTDC. We don't have it here. It's in development. So we have another box like this, which is not powered. It's simply used as a USB, as a SAS to USB-C converter. Then you have a adapter which simply changes. The USB-C cable is one which has the RX and TX lines swapped. So this adapter makes swap again. So we have another USB-C connector, and then you have an adapter which simply makes a fan out to SMAs. To connect these two, there is description on it. You can connect the detector output 1 and 2 to the scope, and that's it. It works. If you want to change the threshold, you simply, there is a command. Command is there is some quick manual on a GitHub how to control the voltage. You need to copy this AFE DRV line and to the terminal. So if you have command like this, it will set 52 and 52 volts. So now effect. Let's switch. Let's set 50-50. And see what happens when you have 50-50. See, it stopped. So 50 volt is not enough for the silicon photomultiplier to multiply the charge. Let's change the threshold. Simply nothing. The scope does not trigger. If we type Ctrl D, it will reload original settings. Something wrong? No. It will reload original settings, and here we are, and it triggers again. So that's it. This is how it works.